Welcome to RCast, the official podcast to the RChain Cooperative. RChain is a complete, concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. Beyond our platform, our investment partner, Reflective Ventures, funds organizations that are working within our core mission statement to create a better world by enabling social coordination in robust, secure, and scalable ways. I'm Derek Barris, the Director of Content for RChain. Each week on RCast, I'll be talking with the founders of our portfolio companies, as well as co-op members, staff, and other figures in the RChain ecosystem about the most pressing issues in blockchain today. Please check out rchain.coop to learn more about the platform, our community, validator sale, and information on becoming a member.
One way to characterize the delta between what we'll talk about today and what we talked about last time is that the building blocks that we were using to ring changes on the different calculi were all related to the structure of the terms. So we were looking almost entirely structurally at the kinds of things that could be rewritten, but we weren't looking at the rewrite stuff itself. And that also provides a source of building blocks to build new calculi. And in fact, it's in many ways, it's one of the things that distinguishes this approach to the notion of dynamics from what has traditionally been developed within classical mathematics. So, and it's kind of important to understand this if you really want to understand how there's been this very, very dominant paradigm that's held sway for several hundred years in terms of how we think about systems that have behavior. You know, whether we're talking natural systems like the gravitational effects of the moon on the tides, or fluid dynamics, or the kinds of actions we see in the cell signaling regime. All of those have been treated in a particular way when people have thought about them mathematically. But when people think about computation, since the 1930s, there's been a sort of a different sense of what dynamics look like and feel like. To set the stage, let me talk about some standard algebraic structures that have been used to model dynamics. So there are algebraic structures called monoids, which there are different ways to conceive them. But one way to that an ordinary listener might think about this is in terms of things like clocks. A lot of times these days people look at digital clocks, but if you imagine an analog clock with a round face and hands moving around, we kind of know what it means to do certain kinds of movement around that face and understand that there's a cycle, right? So if it's 1 p.m. in the afternoon and we go 3 hours, if it's let's say 11 in the morning, and we go 3 hours forward, then we cross the barrier of 12 and reset things and get back to 2. If we go 3 hours from 11 in the morning to 2 in the afternoon, right? So there's a cyclical nature or a modular nature to those kinds of systems that have behavior. We also see that kind of cyclical or modular behavior in some ways when we look at waveforms, right? So there's a kind of cyclical nature to a sine wave that shows up, and that's one way of thinking about it, and that gives rise to a notion of a monoid, and a monoid gives rise to a notion of a group. So monoids don't necessarily have undo kinds of behaviors. You could certainly wind the clock back, but we normally think of time as running forward. So there's not necessarily an undo behavior, But in groups, for every kind of behavior, there's an undo behavior. So groups are a really natural notion of transaction, or at least transactions that can be undone. If you have non-reversible behavior, so if you press the button and the missile gets fired, there's no undo on that. Maybe you could fire another missile and hit that one, but that's a different kind of approach to the transactional behavior. That's sort of preventing the transaction from completing, as opposed to the transaction is complete and we can undo it. So groups provide this kind of idea. And there are a wide range of different notions, all the way up to vector space and things that can be built on top of vector spaces. And vector spaces are very, very typically used in physics. And what I want to say about all these data structures is that the way we think about the dynamics is not really in the data structures themselves. We think about the dynamics most frequently as functions between these data structures. So in particular, in physics, the dynamics are not captured by the vectors. The dynamics are captured by linear functions from one vector space to another, or other kinds of functions from one vector space to another. And that gives rise to a certain way of thinking about the world. It actually colors the way people think about the world. And in particular, it's directly related to these computational calculi. So when we, as Christian, could confirm, when we talk about categories, we talk about gadgets and some kind of structure or information preserving morphism between these gadgets. So we can think about a category of vector spaces, right? So I've got a vector space, and then I can look at some kind of function from one vector space to another, and all the dynamics that we use to model dynamics in physical systems lives in those morphisms and not in the vector space gadget itself. So that has a very strong implication in terms of what's being preserved versus what's where the dynamics are. But when you look at calculi like the lambda calculus or the pi calculus or any of these other things, the dynamics are included in the structure. Last time we spoke, we talked about different kinds of calculi that are built off of different term structures, right? So we were looking at different ways that we could form processes from some core building blocks like names.
Yeah.
But the dynamics with the calculus and what makes it a calculus in some sense, or makes it a computational calculus, is that you have these rewrites that take one process shape to another. So in the case of the row calculus, if you've got output meeting input or input meeting output, then that reduces to the continuation of the input along with the application of a substitution. If you are going to consider different calculi, right, and that's what we were doing in the last time, we were considering a range of different calculi, then you might want to consider a category of these different calculi to kind of organize your thinking, right? But now when you talk about what has to be preserved from one calculus to another, you have to preserve the rewrite dynamics, because the rewrites are packaged with the calculus, with the algebraic gadget comes this rewrite. And so now figuring out what is preserved in the rewrite is a very interesting question. Let me just stop there and just check in with Isaac and Christian and see if my rambling makes some sense.
Yes, it does. It's an interesting question. It's a little bit distinct from the categorical perspective, like you said. I'm wondering if what you're talking about is related to something like bisimulation, or
bisimulation is the notion of equivalence that naturally arises on top of rewrite systems.
Mm-hmm.
you could actually find a notion of biosimulation inside a category, right? You could look at, trees of morphisms and talk about, relationships between trees of morphisms. So if you think of each morphism as effectively a kind of rewrite, but categories, impose these extra equations or relationships on top of the morphisms. So it erases certain intentional structure. But you could still look at, if I start from a particular object or a particular collection of objects, and then I look at all the morphisms coming out of them, I could think of that as a structured tree that is a rewrite system. And then I can ask if there's another tree living in that same category, and if they have this biosimulation relationship. But that orientation is wrong with respect to Curry-Howard, right? Mm-hmm. Curry-Howard is going to ask that our computations are the morphisms.
Yeah.
So computation really, I just don't think people understand this because there's so much siloed thinking. But people do not understand how differently computation thinks about dynamics. And the reason this is important is because we've had this kind of reign of the sort of the Newtonian, Laplacian, Lagrangian view of dynamical systems that has been very dominant in physics and other ways of chemistry, biology. But the fact of the matter is computation does not take that perspective at all. It is really different in terms of the way it thinks about dynamics. Mm-hmm. And then when we look at the kinds of challenges that we find in physics, it might be that the computational perspective provides better tools. So, so the really glaring problem in physics is, of course, the disconnect between the small and the large. General relativity is somehow conceptually disconnected from quantum mechanics. Mm-hmm. And intriguingly, the computational dynamics are scale invariant, right? They have a kind of fractal shape to them that looks like it might be a direction in which that problem is resolved. Just getting the lineup, this broad strokes lineup of the two notions of dynamics are really important, right? Because currently, I don't think it's well understood in either community how fundamentally differently these two communities think about dynamics.
Yeah, that really makes sense because, in your example of like vector spaces or groups or something like that, you've totally separated the structure, like the static structure, from the actual like dynamics of the system. Whereas in these computational calculi, all of that's just mixed into one bag and you get everything all at the same time.
That's right.
So yeah. So it seems, I guess it's obvious in a sense that the question of like, how do you treat those dynamics would be radically different. And then like, what exactly is the important thing to focus on is of course another, interesting question.
Exactly. And so now we can, I want to provide one other motivation, which is very, very physical and practical, and then talk about how at a minimum, Rho provides a really interesting approach to the dynamical part of this, and contrast it to some of the other attempts that have been pursued by people like Milner and Leifer and Ole Jensen and others. Back in the day, so 2002, I had hired Satnam Singh from Xilinx, where he was the CTO, into Microsoft to work on a little project I was working on, where we were building a PyCalculus execution environment and a programming language based on the PyCalculus called Highwire. At that point, I was just privately with other people sharing this idea, the Rho calculus, but I wasn't using that at all inside Microsoft. We were still very, very much committed to the PyCalculus as the core model of execution. And Satnam and Alan Brown, who's a genius logician, and Jan Gray, who's a Harvard guy as well. We all got together, and for the 2002 Think Week or 2003 Think Week, we built a pi calculus chip that we could render on an FPGA surface. And one of the things that Satnam observed was that the size of the chip, the surface area of the chip relative to the surface area of the FPGAs of that time was relatively small. Genius that he is, he said, well, why don't we just tile the FPGA with these chips, right? And he came up with a kind of cool tiling algorithm. But as soon as you do that, the next thing you think about is, well, I've got this steady stream of work coming in. Back then, XML was still a big thing, and I showed that there was an interesting encoding of XML into pi calculus, and that you could use certain pi tricks to do some XML processing. And so you could imagine, a work stream of XML structured data coming in. And then how do you assign that workload to particular chips on the FPGA? And this is a non-trivial problem. Scheduling in general are non-trivial problems, all the way to the traveling salesman problem. But an interesting thought occurred to me, which was there was another calculus, the ambient calculus, which is kind of good at getting work into the right region, right? So it's more of a tree calculus or a tree rewrite calculus. It doesn't even work by substitution. It works by rewriting whole trees built from the terms. And the thought would be that you use an ambient calculus to assign the work to leaf nodes in your tree. So you organize your tiling as if it were a tree, and then interior nodes their only job is to get work out to leaf nodes, and then you have an assignment of what's a leaf to what's an interior based on a notion of tiling. So this is the rough shape of the idea, but now you want to ask about the correctness of the end-to-end system. And that means that you now want to reason about this combination, this sort of uber calculus, which combines the ambient calculus with the pi calculus. And that is a really non-trivial problem. Like people don't even know really, we don't have a nice theory which in detail works out how to reason about correctness in these kind of composite calculi. And that gives rise to the motivation of the sort of thing that Robin Milner was considering at the time, which was a formalism called bigraphs, in which he was looking at a way to sort of, combine calculi. And so now if you think about the talk that we had last time, we were looking at calculi that arose from building blocks, but we didn't look at the dynamics. And now the dynamics are right in our face if we want to reason about this kind of composite ambient calculus, pi calculus kind of thing. And so let me just stop there and just check in and see, does the motivation make sense to folks?
Yeah. So let me just try to clarify the picture that we're thinking about. So you're saying that we have like some sort of tiling or some sort of arrangement of these chips, and some of them are designated as leaf chips or whatever. Some of them are designated kind of more as like higher level nodes. And so the nodes will receive whatever the workflow is, using the ambient calculus, somehow decide which leaf node it should pass that work to. Yes. And then they'll resolve whatever they need to resolve, right?
That's exactly right.
Okay, great. Yeah, that's really interesting.
So I wanted to add something about this idea of going from these static mathematical structures with the dynamics being represented with morphisms between them. It seems like in recent years in like mathematical computer science, this idea of thinking of computational languages as enriched algebraic theories where you weaken equations such as associativity to an actual associator within the theory, it seems like that is what is putting dynamics internal to the language itself. And that's the translation into the mathematical world, that now if we want a proper notion of a of a morphism between different languages that not only changes the structure of the terms, but the structure of the rewrites, then it's going to be about this going from a 1 category to a 2 category. It's preserving the rewrites also.
Yes, exactly. And if you look at the direction that the bigraphs work took, it was just a few years in when they realized that the 2 categorical structure is a much, or some kind of higher categorical structure is more likely to bear fruit in this regard.
Yeah.
I'll be honest, I think a lot of people find that the bigraphs work is non-trivial to work with. Your calculations are not quite straightforward. I remember when I spoke with Robin in that time frame, he said he was doing the hardest mathematics he'd ever done. What Robin finds hard, maybe others might find especially challenging. In many ways, like the row calculus came out of my rebellion that functor categories are probably not the right solution if we want to, provide a name-free notion to software engineers who are not yet familiar with category theory, right? So in some sense, the row calculus represents a naive way of getting rid of names in the pi calculus without a lot of extra categorical machinery. In a similar vein, I tackled this idea of composing systems. So I started with a simplifying assumption. And my simplifying assumption is I'm going to keep the term structure the same. So I'm not going to look at, how to turn pi terms into lambda terms and then somehow preserve, pi rewrites as lambda rewrites. I'm not going to look at some mapping of pi terms into ambient terms or ambient terms into pi terms and then figure out how to preserve rewrites across that gap. I'm going to leave the term structure the same. So my morphisms, they don't take us outside of the domain of our term gadget, whatever it is. And then the question is, can I just isolate the dynamics and think about that compositional structure in the dynamics? There's a very natural metaphor that I came up with that goes back to a sort of a folklore kind of thing, the whole butterfly flapping its wings and that relationship to a hurricane. It also shows up when we talk about biological systems. So for example, if you look at a cell is signaling. The signaling regime from the cytoplasm down to the nucleus is happening on extremely compressed timescales, like femtoseconds, really, really fast. Whereas the production of proteins inside the nucleus, so reading some section of the DNA and assembling the proteins on the basis of that read is happening in minutes to hours. Those are really, really widely separated timescales. And yet, in the cell, they interact. And it is really hard to get differential equations to work well in that setting, where you've got these sort of grossly different timescales, but you have the dynamics kind of interacting. And another place where we have this kind of idea of different layers of dynamics is in networking protocols. So we're sort of commonly understand that HTTP runs on top of TCP, and TCP runs on top of another layer protocol, and we understand what it would be like to connect an application that speaks raw TCP with an application that speaks HTTP. We understand that kind of protocol impedance matching. Does that make sense to you guys?
Yeah.
I think
Yeah,
so.
I'm just thinking back to the material you were talking about in your computational calculi course about how to actually do this translation in terms of different calculi.
Yes.
Different COM rules for the calculus.
Yeah, and that's exactly what I wanted to bring to light. But in the context of this idea of assembling, basically design level thinking about calculus, calculi, right? So last time we talked about design level thinking, which gave us some building blocks to explore different calculi design. And now I want to give another set of Tinker Toys, which are basically these contexts and what they do for us in terms of giving us building blocks for the COM rules.
So you're talking about like the challenge of how to translate between languages that think on very different scales or something along those lines?
Well, I'm really just talking about the combination of COM rules or dynamics.
Uh-huh.
I'm just opening up OmniGraffle right now, and I'm going to make a slide that I will have be available, and it will help me just talk it through as we're going. If we think about the ordinary COM rule in the row calculus, it's the one rule that doesn't have a hypothesis. The struct rule has a hypothesis that, you know, P reduces to P prime, and the par rule has a hypothesis that P reduces to P prime. But the COM rule has no hypothesis. You can just, if you can recognize the left-hand side of the COM rule, you can rewrite to the right-hand side. And that COM rule is, you know, in the row calculus, it's you know, it's of the form, I've got some for comprehension. So for, you know, y from x, so I'm reading some value which I'm going to store in y from the channel x. Whenever that value is available, I will run p with y appropriately filled in with the value I read, and I'm running that in parallel with some process that is outputting, let's say the code of the process Q. Well, it's really outputting Q, but it will be received as the code. So on X, so it's writing on X Q, and the other process is reading from X and stuffing that into Y.
Mm-hmm.
When I do the rewrite in the ordinary row calculus, I get that P, that par is rewritten to P, in which I substitute the code of Q for Y, you know, inside the body of P. So that's our basic COM rule. But we could make a different COM rule. And that COM rule, let's imagine that we have a notion of context. So here, a context is going to be any process term that I have poked a hole in. So for example, in the case of a for comprehension, where we have the continuation P, I could put a hole there instead. Or in the case of an output where we have the process Q, I could put a hole there. Or in the case of a par, I could knock out one side of the par or the other.
To be filled with the process later, right?
Right, exactly. And then I can define a notion of applying a context to a process, which is just filling the hole with the process. So if I use K to range over contexts and P to range over processes, then K of P is just going to be the process in which the hole is replaced by P in K. Mm-hmm. So it's another kind of substitution, and since row is higher order, right, we can pass processes around. We have a pretty clear way we could interpret context directly in the calculus if we so desired. Every context can be turned into a for comprehension because we can, substitute processes into or we can send processes along channels. All right, so now instead of substituting the code of Q, what I could do is, given a context K, put Q into K, and then take the code of that and substitute that for Y. And the interesting point about that is that we can now interpret this context K as providing some kind of impedance match. So we're putting Q into the body of P, but maybe Q is at the wrong level. It's at the wrong scale, or it's not at the right point in the protocol stack. So we need to do some kind of translation, and the context represents that kind of impedance matching. Does that make sense to you guys?
Yeah, I think so. So you would pick out for the given COM rule, are you fixing a given context that?
Yeah, so for each context we'll produce a new COM rule.
Oh, okay. Okay.
But now notice that if I have two of them, let's say I have com k sub 1 and com k sub 2.
Mm-hmm.
Because we have this substitution structure, we can now compose. I could compose com k sub 1 with com k sub 2 by composing the contexts, right? So
yes. So this is kind of like, so each context would be a translation into maybe, I guess the example I'm thinking is like IP TCP. So like one context could be the translation into TCP, one context could be the translation into IP, and now you're saying we can compose these things. So if we have a translation into one, you can then go back to the original and then translate it to the other if you wanted to.
that's exactly right. And in fact, this can give us a notion of morphism, right? So we can build for each of the different kinds of calculi that we considered last time. We can build the notion of context, and now we can build a notion of COM rule associated with that. And now we can get a category that is where any one object in there is, one of these things equipped with this COM rule. And now you can talk about what is structure preserving in this case, and how to do composition of dynamics in this case. Does that make sense?
Yeah, so you're saying because the dynamics are kind of baked into the model already, now having this notion of like composing COM rules given different contexts, we can sort of extend this notion of morphism to include the COM rules, or maybe.
Yeah, exactly. So you can talk about structure preservation and exactly what it is you're preserving. So now you have a notion of a notion of morphism that arises just directly from this notion of the composition of the dynamics.
Isn't it?
So you can backfill a notion of morphism that is structure preserving because you have this notion of composition.
Mm-hmm. So you're considering, are the COM rules the morphisms?
The COM rules dictate your morphisms.
Mm-hmm.
Yeah.
So the COM rules are now something the morphisms will need to preserve, right?
Exactly. That's correct.
Yeah. Okay.
That is precisely the idea.
Mm-hmm.
And so now at least, this is much more restricted in general than the scope that Robin Milner was considering with bicategories. But now at least I have this natural setting in which I've clearly got a notion of how to decompose dynamics.
Mm-hmm.
And therefore, I have a notion of what structure I want to preserve in terms of dynamics. Right? So it's effectively going to be, some kind of structure preservation on the context.
Sorry. So are we talking about a category of calculi?
That's right. It's a category of calculi.
And which structure exactly are you preserving?
So you can now do a structure on the terms that you want to preserve,
mm-hmm.
and which extends to structure on the context that you want to preserve.
Mm-hmm.
Yeah.
Okay. And what would that look like? Like, what is the structure on the? How are you breaking down the structure exactly?
Well, the structure of the context is derived exactly from structure of terms.
Yeah. As a tree structure, like
exactly.
How you built up the term. Yeah.
That's right.
Okay.
That's right. So now we have a notion of morphism, which allows us to build a notion of category, and then we could potentially loosen this to allowing different term structures. But it's more complicated, right? I mean, it's going to dramatically increase the complexity. But the technique of using context-based COM rules is widely applicable. You could do the same thing to the lambda calculus.
Okay.
Right? So instead of doing a direct substitution, you apply a context to the term before you do the substitution.
Mm-hmm.
Right. So the technique is actually broader than just the row calculus. Does this make sense?
Yeah, this is really nice.
I'm trying to make a couple of different points. So for the R-chain community, the person who's interested in that, again, the row calculus is sitting in a larger context that allows us to explore in a mathematically rigorous way a wide range of different computational dynamics for our smart contracting language. And in particular, what this gives us is we can imagine that there's a whole giant application protocol stack that grows up around RChain. Let's say that we build a rich music application, and that music application has a whole protocol embedded in it that is entirely at the business level, right? And now we want to talk about the interaction of that protocol dynamics with the protocol dynamics associated with, let's say, a social network dApp that's also built on top of RChain. Now we can talk about the end-to-end correctness of the dynamics in the music app as it fits the dynamics in the social media app, right? Using this technique. And that's really important because we have to be able to build correctness in a step-by-step fashion. Like, we can't assume like that we have this God's eye view of all the applications that have ever been built or all the variations of the protocol that are ever going to be, rolled out. We can't do that. So we have to be able to do these piecemeal semantics, compositional semantics that allows us to do end-to-end correctness. And that's why this kind of technology is so important.
Does this also allow for like modularity with the rules that you're using? Like, could we take some protocol developed, like, say, maybe for a music app specifically, and then take that into like another one just by composing the protocol with whatever it is that we're currently looking at?
Yes, that's the idea. That's it. And it's also important, right? Because when we think, it's not just at the app level, right? We know that we're going to be rolling out different versions of the protocol, right? Over time, the protocol will evolve because we'll fix bugs, or we'll find optimizations, or the market conditions will change, and we have to respond to new market requirements. So all of those things are going to put a pressure on the protocol to evolve. But not every validator will accept every change, right? The validators are going to go, well, I'm sorry, but right now, smart contracts in this version are much more lucrative than the one that you're proposing. So I'm not. But others may take a more future-oriented look and say, oh yeah, we're really excited about those kinds of changes, so we're rolling those out immediately. And so now you have heterogeneous networks, and still want to be able to reason about the correctness of contracts that run end to end.
And maybe a pretty important point to make here is just the ability to change the protocol just by being able to have this modularity and make small changes without going back and totally changing everything from the beginning can make just slightly modifying things much easier.
Yeah, exactly. That's another piece of the puzzle. I also think that this gives us a really interesting way to begin to look at some of these other physical dynamics, and that's why I started with some of those metaphors, right? The whole butterfly wings, hurricane metaphor. I think that there's something here in the computational way, that the computational view of dynamics, that can say a lot to physics and chemistry and biology. I got interested in modeling very, very simple physical systems like knots. And they have a crisp, clear interpretation in terms of the process calculi. But you can go quite a bit further. You can definitely encode notions of location, and these are very abstract notions of location that have a much wider range of application than we typically find with metric spaces. My sense is that there needs to be a fairly energetic conversation about how these kinds of tools and techniques can help the application of, mathematics to physics and to the physical sciences in general.
Mm-hmm.
So you're saying that this parameterization of processes or of the communication rules by context is going to serve as the primary link between languages, because it's going to suffice that if you have a certain rewrite in one language, there's always going to be a way to translate it to not exactly a primitive rewrite in the other language, but if you encapsulate it in this bigger context, it's always going to be valid and meaningful in the other language?
Well, I'm not saying that it's always going to be valid. What I am saying is that this is a reasonable first guess as to the kind of discipline that you might want to impose. So it's only been in the last 30 years that we've had a notion of sort of gold standard programming language semantics or computational dynamics comparison of behavior. So specifically, the notion of full abstraction was only put forward in the late 80s, early 90s. So full abstraction, basically says, if I have two computational systems, Calculi or some other kind of system, and I have an interpretation from one to the other, it's got to be the case that let's say P and Q are two different computations in system one, and we can talk about their translations in system two. Then if P and Q are equivalent in the first system, then their translations need to be equivalent in the second system, and vice versa. So this is our notion of full abstraction. It's obviously inspired by similar kinds of notions of equivalence in category theory, but this is the first time that we've had this kind of gold standard. And there are lots and lots of interesting systems that are not related by full abstraction. So, for example, pi calculus, to date, there has been no fully abstract encoding of the ambient calculus into the pi calculus, which strongly suggests that there's a higher degree of expressiveness in the ambient calculus than in the pi calculus.
Mm-hmm. So is there an encoding of the pi calculus into the ambient calculus then?
That's easier to do.
That's easier to do. Okay.
Yeah. So likewise, there is no par preserving encoding of mixed output into the asynchronous pi calculus, with the input guarded sum. And so it's very clear that there's some kind of expressiveness in mixed summation settings that just doesn't occur. But this and now to bring it full circle to your answer to your question, this notion of context can give us a wider spectrum of comparison. So we can talk about things that are not fully abstract, but that do have a context-based encoding, that it's fully abstract up to the context.
Yeah.
Right? That widens the discussion of the comparison of dynamics.
Yeah. Has anything been done like this before?
To the best of my knowledge, this is the first time ever I've talked about these things. I have notebooks and notebooks and notebooks filled with results that I've never talked about in public.
Great. Well, thanks.
But I think it's really important. So I'm trying to say that, like, for the R-chain community, this is what they're getting when they bet on RoCalc.
Mm-hmm.
It's not just this one calculus. It's this much, much wider array of tools and techniques that we can employ over the lifetime of the chain.
Mm-hmm.
My hope is that it's not just our chain that this has applicability to, but a much wider setting or set of challenges that face us, both in terms of physics and in terms of just computer science, right?
So you said the ambient calculus is probably more expressive than the pi calculus. Does it have a fully abstract embedding into the row calculus?
I've given an encoding. I haven't ever proved that it's fully abstract, but intuitively, it looks fully abstract.
Yeah.
But we have a lot of extra machinery in the row calculus than we do in the pi calculus.
I don't know much about the ambient calculus, but it seems somewhat similar to this idea because it's based on having the notion of context kind of built in. Yeah,
it's full tree rewrite, right? You actually, you don't do substitution. You actually rewrite the tree.
Yeah.
So that's, this is a really interesting idea in and of itself. But like if rolling it out over a network, right, you're potentially doing whole network rewrites, and that's you could kind of see why that's a lot harder.
Yeah.
Even if you virtualize the network, it's still it's a lot harder and requires a lot more cooperation amongst the nodes in the network that are affecting those computations. Cool.
Well, I hope you start sharing all these results.
Yeah.
Well, step by step, right? There has to be. I think what I found is that each of us has our own sort of passions and pursuits and projects, and to lend attention to someone else's stuff, there's got to be a motivation.
Yeah.
So step by step, what I've been doing is to create a network of motivations that makes it worthwhile to go and look at these kinds of results.